We have already learnt about simple bonding models, where chemical bonds can be classified as ionic, covalent, or metallic, and that the nature of chemical bonds influences the physical and chemical properties of substances. Ionic bonds only occur in ionic solids and are very strong electrostatic forces of attraction between oppositely charged ions. Large amounts of energy are required to overcome these forces, giving these substances high melting points. Covalent bonds are strong electrostatic forces of attraction between a shared pair of electrons and the positive nuclei of two adjacent non-metal atoms. When the electrons are equally shared, the bond is non-polar covalent, and the lack of dipoles results in weak intermolecular forces and low melting points. When the bonding electrons are not equally shared, the bond is polar covalent, and the resulting dipoles cause stronger intermolecular forces and higher melting points. Metallic bonds are strong electrostatic forces of attraction between a lattice of positive ions and their delocalized valence electrons. These bonds produce the typical metallic properties such as ductility, malleability, high melting point, and electrical conductivity. These simplified bonding models can be useful to explain physical and chemical properties of elements and compounds. However, all oversimplified models have limitations and do not apply in every circumstance. For example, aluminium chloride is predicted to be ionic since it consists of a metal and a nonmetal. However, it has a much lower melting point than other traditional ionic compounds. This suggests that aluminium chloride is not only ionic as predicted, but has some covalent nature too. To account for these inconsistencies, we can revise our understanding of bonding and imagine a line where different types of bonds between atoms are placed based on how they share or transfer electrons. This line is called a bonding continuum. At one end of the line we have ionic bonds, where one atom completely gives up one or more electrons to another atom to form a cation and an anion. At the other end we have non-polar covalent bonds, where atoms share electrons equally. In between these two extremes there are polar covalent bonds, where the electrons are shared but not equally. This continuum helps us understand that bonds aren't just one type or another, but can have characteristics that fall somewhere in between. The limitation of this bonding continuum line, however, is that it doesn't include metallic bonding. So instead, we can think of a triangle that shows the relationship between different types of bonds, this time also including metallic bonds. Each corner of the triangle represents one type of bonding. Inside the triangle, we can place different compounds depending on how their bonds behave. For example, a compound with bonds that are mostly ionic but have some covalent character will be placed closer to the ionic corner, but not exactly at it. This triangle helps us visualize that most real-world bonds are a mix of different types, not purely one or the other. Where an element or compound is located on the triangle depends on the electronegativities of the elements. This triangle shows the electronegativity difference on the y-axis and the average electronegativity on the x-axis. This is the symbol for electronegativity, the Greek letter He. The electronegativity difference between two elements A and B in a bond can be calculated using He A minus He B. And the average electronegativity is given by the sum of the electronegativities of the two atoms in the bond divided by 2. Compounds with an intermediate to large electronegativity difference are ionic and are located towards the center of the triangle or near the apex. Compounds with a small electronegativity difference, and which are thus nonpolar covalent, are located towards the bottom right. When this electronegativity difference is slightly larger, they are located near the middle of the triangle in the polar covalent region. Percentages placed on the right-hand side of the triangle can be used to determine the relative percentages of ionic or covalent character. Pure elements have an electronegativity difference of 0, and so elements are located on the x-axis at a position equal to their electronegativity. Finding the electronegativity difference of two magnesium atoms in elemental magnesium is 0. Therefore, magnesium will be found along the x-axis. The same is true for chlorine. From the average electronegativity calculation, we will find magnesium is placed at a value of 1.3 on the x-axis and chlorine at 3.2. We can see magnesium is located in the metallic region and chlorine in the covalent region with 100% covalent, or we could say nonpolar covalent nature. For the binary compound magnesium chloride, the electronegativity difference between magnesium and chlorine is 1.9, which is its y-axis value or coordinate. The average electronegativity between magnesium and chlorine is 2.25, which is the x-axis value or coordinate. Using the coordinates, we can locate magnesium chloride in the ionic region. Using the percentages on the right-hand side allows us to deduce that magnesium chloride is approximately 60% ionic, but it does also have some covalent character. Knowing the percentage of bonding types allows us to predict the properties of a substance. Elemental magnesium in the metallic region is predicted to have typical properties of metals: high melting point, malleability, ductility, electrical conductivity, and so on. While elemental chlorine, being nonpolar covalent, is predicted to have typical non-metal element properties, such as low melting point, boiling point, and poor electrical conductivity. What about magnesium chloride? Since magnesium chloride is approximately 60% ionic, we can deduce that it will have a high melting point, but not as high as a substance whose ionic character is more than 60%. If we were to do the same calculations for sodium chloride, we could locate it higher on the triangle at an ionic character of about 74%. Since sodium chloride is more ionic in nature than magnesium chloride, we can deduce that it would have a higher melting point. Now let's turn our attention to two types of materials, alloys and polymers. We'll start with alloys. The unique and useful properties of two or more different metals can be combined by mixing the different metals into one material called an alloy. An alloy is a homogeneous mixture of two or more metals, or sometimes a metal with a nonmetal. Often an alloy has superior properties to the pure elements. This mixture is usually produced by mixing the component elements in a specific ratio and heating in a furnace. Melting forms a homogeneous solution which then cools and solidifies. The constituents in this solid solution are mixed together physically, with metallic bonds holding the particles together in all directions. The particles are not chemically bonded. A chemical reaction does not occur when forming an alloy, and so the individual constituents retain their individual properties. Since metallic bonds are non-directional, this allows different elements with different sized particles to mix. The different sizes of the ions in the lattice cause the lattice to be distorted relative to the rigid and orderly lattice of a pure metal. The nature of the constituents and their properties, and the way in which the lattice distorts, produces new properties such as improved hardness, strength, and resistance to corrosion. For example, lattice disruption due to unequal particle sizes makes it harder for particles to slide over each other, resulting in a harder material than a pure metal, where the layers slide more easily. Common examples of alloys include steel, which is a mixture of iron and carbon. Steel is stronger than pure iron, giving it usefulness in certain applications such as a building material. Stainless steel also includes a small quantity of chromium and nickel, which makes this alloy corrosion resistant and perfect for use in a kettle, for example, where it won't rust. Brass and bronze are copper alloys, and they are harder than their pure element constituents, as well as corrosion resistant. Polymers are large molecules formed by covalently joining 50 or more smaller molecules together. This type of reaction is called a polymerization reaction. Each repeating unit in a polymer is called a monomer. Due to their size, polymers are also known as macromolecules, as they are significantly larger than other molecules. Polymers which consist of only one type of monomer are called homopolymers. Those which consist of two or more different types of monomers are called copolymers. Many biological molecules are polymers. These natural polymers include proteins, which are made from different amino acid monomers, and DNA, which is composed of monomers called nucleotides. Examples of synthetic or man-made polymers are plastics. There are many types of plastics which we use in our everyday lives. The properties of a plastic polymer, and any other polymer for that matter, are influenced by the nature or identity of the monomers, the length of the polymer chain, and whether the chains have branching or cross links. So, the structure of a polymer determines its properties. Let's investigate the common properties of most plastic polymers and see how these properties are derived from their chemical structures. Saturated plastic polymer chains contain no double bond functional groups available to react, making such plastics unreactive. Loose packing of chains results in lower density than other materials such as metals. And the more branched a polymer is, the more lightweight it is. The many covalent carbon-hydrogen chains and branches in a plastic polymer cause plastics to be hydrophobic, that is, they repel water molecules. And so most plastics tend to be water resistant or water repellent. The strong covalent bonds between monomers in the chain, added to the way in which chains stack or wrap around each other, or even cross-link, make plastic polymers strong. These are the common properties of most plastics. Different plastics, however, have slightly different properties based on their unique chemical structures. For example, polyethylene, which is composed of ethene monomers, is relatively low in mechanical strength but is flexible. While polychloroethene, or PVC for short, which is made by bonding chloroethene molecules together, is strong and rigid but more brittle than polyethylene. Because plastics tend to be unreactive, this makes them non-biodegradable. Pollution from the accumulation of plastics in natural environments is an important environmental concern. Some polymers are made by a type of reaction called addition polymerization. During addition polymerization, many smaller unsaturated monomers react together to form one larger molecule, an addition polymer. For example, polyethylene is formed when the pi bonds in the ethene monomers break and the units bond together, forming new carbon-carbon single bonds. We can represent the many repeating units of the polymer with brackets, and the letter N indicating the number of monomers used to make the polymer. The formation of polychloroethene from its monomer chloroethene also occurs by an addition polymerization reaction. If we are given an addition polymer structure, such as this one, we can deduce the repeating unit and the monomer. These are the repeating units. Writing just the repeated unit with a subscript N gives us the shorthand for the polymer, and without the subscript N we have just the repeated unit structure. The monomer will have the same atoms as the repeated unit, except that it is unsaturated. This molecule happens to be styrene, and the polymer is polystyrene, formed in this addition polymerization reaction. Polystyrene that has been expanded with air we call styrofoam, which is commonly used in packaging. Let's now summarize the key points. The type of bond between two atoms is best understood as a continuum rather than just covalent, ionic, or metallic. Electronegativity values and a bonding triangle can be used to deduce the degree of ionic, metallic, or covalent character for a binary compound, and from this, its properties can be predicted and explained. An alloy is a homogeneous mixture of two or more metals, or a metal with a nonmetal. Often, an alloy has superior properties to the pure elements due to distortions in the metallic lattice. Polymers are macromolecules composed of the same or different monomers. The properties of plastic polymers, including their low weight, strength, and unreactivity, arise from the chemical structure of the polymer chains. In an addition polymerization reaction, the polymer is formed when the pi bond in the unsaturated monomers opens up to form two new carbon-carbon single bonds.